I'd like to start the talk off just by reflecting a little bit about hardware performance. A lot of our motivation here is very similar to Arrakis, so I'm not going to go into too many details here, but let's just take a look at kind of an illustrative example just to see like what the hardware capabilities really are. So we're assuming 10 gigabit Ethernet. This is widely deployed everywhere. And if we were going to perform a 64-byte TCP echo, then we can get some pretty impressive performance just with this raw hardware. So in terms of latency, round trip times on the order of 10 microseconds are readily achievable inside a rack. Actually, the latency inside of a data center is not much higher than this. And in terms of throughput, for these 64-byte messages, we could actually be pushing almost 9 million requests per second. So these are really huge numbers, but of course, these are just the raw limits of the hardware. So with that in mind, what really happens when we run a full operating system now and we have a whole software network stack? Well, we start to see quite a significant performance gap. Really, we're not able to get anywhere close to the hardware limits when we're running software. And so X is a new kind of operating system that attempts to close this performance gap. And so for this particular benchmark, if we compare against Linux in red here, for X, we're actually able to get very close to these hardware limits, including saturating the NIC for this high throughput 64-byte message workload. And so how do we go about achieving this? Well, we have two kind of orthogonal and high-level contributions. The first is the use of virtualization hardware. And we use it so that we can get efficient access to the network controller, but we do it in a way where we don't sacrifice security or protection. The second is a new execution model. Now that we have access to this hardware, how can we actually use it so that we can get both low latency and high throughput? So I'm going to talk about each of these in more detail during the talk, but sort of an obvious question is why are we writing a new operating system in the first place? So this pretty complex diagram here is from the Linux Foundation, and it actually shows all of the different code paths that we could traverse through the Linux kernel during network processing. And there are kind of two high-level issues that lead to all this complexity. The first is that we have a really complex interface between the application and the kernel. Sockets are everything for everyone. We've got blocking sockets, non-blocking sockets, asynchronous I/O, dozens of set socket ops, etc. And so we have to support a ton of different interfaces, and this leads to complexity. The other issue is we have a lot of really convoluted code paths, and the reason is that there isn't much coordination between the application and the kernel. The kernel network processing is largely driven by interrupts and also scheduling decisions in the kernel. So we're going to take kind of a random walk through this code, and it's really hard to predict which path we're going to take because it depends on the particular situation and the particular arrival times of the interrupts. And so to step back a little bit and extrapolate a little bit further, we think that a lot of these performance issues basically stem from the fact that we're still pretty much using Berkeley sockets, very little has changed in this interface, and we're really designing our kernels for CPU time sharing. But if you look at today's large-scale data center workloads, the motivations are very different now. And so let's talk about two of those issues. The first is hardware has impressive performance. We have really dense multi-cores, 16 cores and beyond, 10 gigabit Ethernet, 40 gigabit Ethernet soon. And so this means that we've got new types of constraints that didn't previously exist. So we need extremely scalable APIs in a multi-core sense. There's a rising gap between compute performance and the memory access latency. And so what this means is that we need really good cache behavior if we're going to get good performance. And packet inter-arrival times, even with 10 gigabit Ethernet, could be as low as 50 nanoseconds. So this is much lower than even the time it would take to service an interrupt. Now on the software side, workloads in the data center are also changing. And we basically have these scale-out access patterns, and this manifests as fan-in and fan-out. In the case of fan-in, we have to deal with a large number of active connections for any given server, and this also leads to a very high request rate. In the case of fan-out, our clients could be making requests to 100 or even 1,000 separate servers, and so the slowest server to respond tends to determine end-to-end performance in the data center. And so tail latency is a very important metric. And so all of these are kind of new constraints that are emerging as we scale out in the data center. And we think for this reason, it's a really exciting time to rethink I/O APIs and to rethink how we implement our network stack. Of course, there have been a lot of different approaches that try to close the performance gap that I showed earlier. They kind of fall into three categories. One thing that we can do is bypass the kernel. We could move everything to user space, or we could put the network stack in hardware. Another issue is that there are many approaches that try to avoid connection scalability bottlenecks because having a large number of active connections can be challenging with TCP. And so we could use something like UDP, or maybe we could use some sort of a proxy as sort of an intermediate layer. And then finally, we could give up on Ethernet altogether. We could use some lossless fabric like InfiniBand, and we could support some advanced hardware features like RDMA. And sort of the common thread in all three of these areas is that they're looking for various ways to bypass or work around system software. With IX, we want to take a very different approach. So we're not going to bypass the kernel. We want to have robust protection between the application and the kernel, so we need that protection boundary. We're not going to avoid connection scalability. We're just going to use TCP, and we're going to architect the system in a way that it scales to a large number of connections. And we're not going to replace Ethernet. We're just going to try to be compatible with commodity 10 gigabit Ethernet, off-the-shelf NICs. And so really, we're going to see if we can tackle the problem head-on by building better systems software. Okay, so I talked a little bit about the motivation and our basic design approach. Now I'm going to circle back to those original two contributions. So the first contribution is this use of virtualization hardware to get efficient access to the network controller, but in a way that doesn't sacrifice security or protection. So what you can see here in this slide is our system diagram, and very similar to Arrakis, we're embracing this control plane and data plane separation. Our control plane does coarse-grained resource management. It allocates entire CPU cores, large memory pages, that sort of thing. And then each of our data planes are given us one or more CPU cores, and each data plane runs a single application. Our data planes, also like Arrakis, are given direct pass-through access to the network hardware. And so they can get very efficient access to the network registers. This is done through memory-mapped I/O. And so there's no overhead imposed by the host kernel. It's just direct access to hardware. Some user-level network stacks also use this approach. So now let's see what's different and what we're doing with virtualization that's kind of unique in IX. So we're leveraging virtualization extensions, in our case VTX, so that we can actually get this extra protection level. And we're going to use this extra protection level to effectively divide the data plane in half. The way that we support this is using a system called Dune. So we could have written a brand new hypervisor from scratch, but the reason that Dune's really beneficial here is now we can run on just an ordinary Linux kernel. The Linux operating system becomes our control plane. And now both our data planes and our control plane process are just ordinary Linux processes. So each data plane has this direct access to hardware, but it can also perform system calls to the Linux kernel. And so this is really convenient. We actually rely on the Linux kernel for file system support, but then at the same time, we can do some really radical innovation for network performance in each of the data planes. So let's talk about this extra security level. How do we actually use it to improve isolation? Well, what we do is we run our application in Ring 3. We also have a user-level library that I'll talk about more. And basically, this application is now completely untrusted. It can't corrupt any of the memory in the network stack, and it can't corrupt the Linux kernel. We then take our data plane operating system that we now call the IX data plane kernel, since it's running in guest ring 0 mode. And now we trust the data plane to adhere to network standards and specifications. So it's going to follow proper TCP flow control. It's going to do congestion management correctly, these sorts of things. But it can't corrupt or manipulate the memory in any other data plane. And then finally, we trust the Linux kernel and our Dune module to provide memory isolation and protection and to isolate these various data planes. And so in this way, we kind of have these 3 layers of separation and security protection. Okay, so I talked about our use of virtualization hardware. Now let's take a look at our second contribution, which is this new kind of execution model that makes it possible for us to get both low latency and high throughput. So I've got kind of a system diagram here of just a single X data plane kernel now, a single X data plane rather. And so we're kind of zooming in from that previous picture. And so we still have these 2 protection modes, the application's running in ring 3. And kind of in stark contrast to that earlier diagram that I showed of the Linux kernel, we're going to do I/O processing in a very different way. So we're going to have this really well-defined order, and we're going to switch between the kernel and the application in a very coordinated manner. Let me walk through some of the steps to build some intuition. So the first thing that we're going to do is we're going to pull the receive ring. We're going to pull off any new packets that have arrived. We're not going to use interrupts in the common case. So pulling is we're going to be able to do normally because of this execution model. Then we're going to do some TCP IP processing. This will produce a series of events. We'll write these events to a scratch buffer, and when we're done with TCP processing, we'll perform a protection domain crossing into user space. From there, we're going to run our application. Our application is an event-driven application. That's the type of workload that we're targeting. And it's going to use libx as sort of a helper library, both to provide a familiar programming model and also to abstract some of the details of our low-level interface. The application is then going to consume all of these events, and it's going to generate a series of system calls in response. It's not going to perform a protection domain crossing for each system call. Instead, it's just going to write the calls into a buffer, and then when it's finished, it's going to do a transition back in the kernel. From there, we're going to do more TCP IP processing, this time to send packets. We're also going to run our timer subsystem so that we can see if we need to retransmit any data. And then finally, we're going to program the transmit ring to actually put the packets on the wire. And so this is kind of the basic flow of execution in our system. Again, we have very explicit transitions between the kernel and the application, and we have this well-defined order of steps that we're going to process things in. So this enables us to take advantage of certain design principles that improve performance. The first design principle is this notion of run to completion. It's this very simple idea that when we receive a packet, we want to process that packet all the way. And that means going all the way through the application and then back into the kernel and potentially transmitting a response if it's appropriate for that packet. This is great for performance for 2 reasons. First of all, it's going to improve data cache locality because we're going to be reusing all the cache lines that were produced from the previous step in each of these stages in the pipeline. The other thing is that we now have this really well-defined order that we're processing things, and we're going to work our way through that order all the way for each packet. So we've effectively removed a lot of the scheduling unpredictability and jitter from the system. So this is also how we're able to get low latency in X. Now there is this question of how many packets should we actually process in each of these steps. And so that brings us to our second design principle, which we call adaptive batching. Now, if we just use batching normally, it could be very harmful for latency because we could wait for a while to batch a group of packets, and that's just going to add to the overall latency of the system. So we use this kind of unique approach that we call adaptive batching, and the way it works at a high level is we're basically only going to batch in the presence of congestion. And so the way we do this is we have this really simple algorithm. We look at our receive buffer, and we're not going to wait at all to perform network processing. So if there's only a single packet in that buffer, then we're just going to process that packet immediately, and we won't do any batching at all. But if there's a buildup or a congestion in that buffer, then we'll batch up to a maximum batch size. The reason that we set an upper limit is that we don't want any one of these steps to take too long because it could starve the transmit queue or otherwise introduce jitter. And so back to kind of our flow through these various steps, now that we're using batching, we're going to grab some subset, maybe all of the packets in our receive queue. We're going to generate a set of events that are appropriate for those packets, now in accordance with this batch size. And then we're going to generate a set of system calls, also batched from user level. So this is good for performance because it means that in each of these pipeline phases, we're able to rerun the same code over and over again for each packet. And so we get very good instruction cache locality this way, good branch prediction behavior, and also because we're now performing regular memory accesses by using the same code segments, the hardware prefetcher is more likely to predict the next cache line as well. Okay, so there are several other design elements in our paper. Because of time constraints, I don't have time to discuss them now, but check out the paper for more details on how we do multi-core scaling and how our API works. There's also more details about libx. It provides a lib event, some interface that's pretty similar to lib event. And we also have a pretty substantial prototype. We're leveraging a bunch of existing code bases, including Dune, DPDK, and LWIP. And it's around 40,000 software lines of code just for our Dataplane kernel alone. Okay, so I talked about our motivation and kind of our design approach. Now let's take a look at performance and kind of conclude with the evaluation section. So we compare X to existing systems, a highly tuned Linux environment, and also MTCP, which is a state-of-the-art user-level network stack from NSDI 2014. We're going to do both micro benchmarks and a Memcached evaluation. And for all of these benchmarks, we're using the TCP IP protocol. I've got a picture right here of our experimental setup. We've got around 25 Linux hosts that we use as load generators. They're all connected together on the same 10 gigabit Ethernet switch. And we have two configurations that we're going to evaluate. One is just a single 10 gigabit Ethernet link, and the other is 4 10 gigabit Ethernet links bonded together, so we have a logical 40 gigabit Ethernet interface. Also, for all these experiments, we're going to use a single CPU core with a single CPU socket, with 8 CPU cores. Okay, so let's get started with some of these benchmarks. So the first benchmark I wanted to talk about is Netpipe, and if you're not familiar with Netpipe, it's this very simple benchmark. We're going to basically synchronously echo packets, and because there's just a single TCP flow here, the workload is largely dominated by latency. And so our half round trip time latency for small packets is on the order of 5.7 microseconds. This is just to build some intuition for why X, which is the black line on the top here, has a performance benefit. A pretty good metric for Netpipe is what size message do you need to echo in order to reach half the theoretical bandwidth. And so with X, this is 20 kilobytes. By comparison, Linux takes 135 kilobytes. And MTCP, at least for the range of echo sizes we evaluated, was never able to reach this point. The reason for this is despite the fact that MTCP can sustain very high throughputs, it has a lot of extra latency because it doesn't use adaptive batching. So just putting a network stack in user space is not necessarily a solution for all types of performance issues. The execution model matters a lot too. Okay, so that was for a single TCP flow. Now let's take a look at what happens when we have multiple TCP flows. So now we have all of those Linux hosts generating load, as I mentioned earlier. And what this graph is showing is the throughput that we can achieve with different numbers of CPU cores. And so kind of the highlight here is that we're able to saturate our 10 gigabit NIC with 3 cores for this TCP echo connection, echo benchmark. These are for short-lived connections in this particular benchmark. And not only that, but for our logical 40 gigabit Ethernet interface, that's the darker black line here, we can actually continue scaling. By contrast, MTCP is also able to saturate a 10 gigabit Ethernet line, but it needs all 8 cores to do so. And of course, Linux is kind of nowhere close for this particular benchmark. All right, so another benchmark that's interesting is connection scalability. So now we're again still going to look at throughput, but this time we're going to vary the number of connections that we use in our load generators. And so what you can see here is that we're able to sustain a really high throughput for a very large number of connections, all the way up to 10,000 connections before we start to get kind of limited by the L3 capacity of our CPU socket, and then we start to get capacity misses. And even then, we can still sustain a pretty good level of performance. All right, so finally, I'd like to wrap up with Memcached performance. This is again over TCP. What you're seeing here is the latency that we can achieve for various throughputs. In the darker line, I'm showing 99th percentile, and the dotted line is average. And kind of the highlights are here are we're able to get 3.6 times more requests per second for our 500 microsecond SLA. This amounts to around 1.8 million requests per second. We're using a workload that's modeled after a paper by Facebook that shows typical access patterns in their data center. We also can reduce tail latency by a factor of 2. This is actually with Linux clients. So we discovered that the Linux clients were actually most of the tail latency overhead. We did another experiment with X clients now on both ends, and we could get tail latency down by as much as 6x compared to Linux. All right, so kind of running out of time, so let's wrap up the talk. Again, this is sort of a protected Dataplane operating system. It's designed for data center applications that have really demanding connection scalability requirements, and we have 2 contributions. The first is this new use of virtualization to get both security and fast access to hardware. The other is this new execution model that makes it possible to get both high throughput and low latency. So with that in mind, thank you very much. Are there any questions?
Hi, Brad Karp, UCL. I enjoyed your talk a great deal. I had a question about data cache locality versus instruction cache locality, both of which you mentioned during your talk. So in the 90s, the networking research community proposed things like integrated layer processing to try to process packets through many layers of the stack to try to improve data cache locality, much like what you were talking about. Are these 2 things in opposition in your system at all? Like, you want to process the same group of packets to get up the stack and through the application to get good data cache locality. But then to get good instruction cache locality, you almost want to do the opposite thing of, looping at 1 bit of code in order to sort of improve instruction cache locality. So I guess I wondered, are these in opposition at all in the system? And also, did you find that you ever encountered instruction cache locality problems as you were doing your work in any workloads that you needed to adapt for?
Yeah, so in general, at least we didn't observe that they were in opposition. One nice thing is that as long as the amount of data that we're building up between these processing phases fits in the L1 or L2 cache, then we can go pretty far with instruction cache locality without sacrificing data cache locality. So I guess that was at least our experience. I'm sorry, what was the second part of the question?
I just wondered, like, did you find that you needed to adjust the granularity of processing for any workloads because you ran into a problem on one side or the other?
Got it, yeah. So as far as adjusting it, this is actually another reason that we need to set an upper batch size. If we go too far with that batch size, then we could actually run into situations where we get worse performance, in part because of these types of effects.
Thanks.
Thank you.
Hey, Adam. Great talk. Simon here, kind of on behalf of the Iraq's team. You mentioned tail latency in your talk, and you had a few numbers there. We also care about tail latency very much, and I should mention that Iraqis has excellent tail behavior. I was wondering if you could say a little bit more about how the batching affects tail behavior of X, especially if you kind of view it into the future with faster and faster Ethernet, like 40 gig and then 100 gig and so forth, where the batches kind of, the congestion becomes larger.
Yeah, so I've got one backup slide that might be interesting. Here's a diagram of actually the effects of batching on Memcached. So this is the same experiment that I was showing earlier. In this case, we're setting different upper bounds for our adaptive batch limit. And so what you can see is that no matter what the batch limit is, at lower throughputs, it has absolutely no impact on latency. The reason is because of the adaptive mechanism, we're not batching at all at those lower throughputs. Now at higher throughputs, we actually get lower latency too. And the reason is that because our stack is more efficient, now that we're enabling batching, we're actually able to reduce head-of-line blocking. So if we didn't batch at all,
we'd be on kind of the exponential part of the curve, and our latency would be spiraling out of control at these higher throughputs. So we're able to carefully balance those two trade-offs using this adaptive mechanism.
Thank you. Excellent talk.
Thank you.
Thank you. Michael Condit, NetApp. Yeah, that was a great talk. Thanks. You mentioned that you use a run-to-completion model. I guess that implies that while the core is in the application processing the incoming network request, no one's listening on the NIC, right?
That's right. While the application is doing processing, that particular NIC queue is not being pulled.
So that's not really practical, is it, for servers that might have a very large variability in request processing time? If they have some requests that take milliseconds,
Yes.
what would you do about that?
Yeah, so
You'll drop requests that the NIC is.
that's right.
When no one's listening.
So we have a notion in our system of both I/O threads and background threads. We're still experimenting with this mechanism, but what we want to do is restructure applications in a way where they write some threads that are designed for I/O processing and other threads that they can defer longer duration work or maybe transfer longer duration work over to. We think that this is an exciting area for future work. And of course, existing systems tend to have a lot of performance problems when they have a very long processing time in the application as well. Another point on this issue is that we would like to make use of interrupts so that we can at least poke our Dataplane kernel and make sure that we're not unnecessarily dropping packets if the delay isn't at least not very long. So we want to be able to do a better job with that trade-off in the future. And we think that interrupts as kind of a fallback instead of the main driving source for I/O are an effective way to address that issue.
Thank you.
Thanks. All right, last question.
Yeah, hi Adam, Steve Muir, Comcast. Interesting stuff, and I don't mind being preempted. That was my first question that the gentleman just asked, so thank you. My other question was sort of one of the challenges sometimes with batching APIs is if you have sort of dependencies between sort of consecutive operations. Have you come across this at all? Sometimes, maybe if, operation N fails in a batch, then, what do you do with the subsequent operations? Is that something that you've kind of thought about at
Yes.
the API level?
Yes. So when we were building and designing our API, which I didn't have time to fully discuss in this talk, that was one of the big issues that we ran into. And through a lot of iteration, we were able to structure our API in a way where we can avoid the one failure impacting the other requests in the batch. We use this sort of heuristic where we basically will only issue one request per network flow. And we're able to actually consolidate a large number of requests per flow. And so a batch is a set of consolidated per flow requests. And so in that way, if one of them fails, it won't keep going through the other requests as part of that flow. Hopefully that makes sense.
Thank you.
Thank you.
Let's thank the speaker.